A reciprocating compressor compresses refrigerant vapor in a cylinder using a piston. In a way, reciprocating compressors are like automobile engines. The pistons are directly driven through a wrist pin and connecting rod from a crankshaft. Depending on their size, reciprocating compressors may have one or more cylinders. Multiple cylinders may be arranged in line, opposed, or in a V. In each cylinder, reciprocating compressors have both a suction valve and a discharge valve. These valves give the compressor its ability to pump refrigerant vapor against a pressure difference. They are usually located in the head of the cylinder, in passages connected to the high or low pressure side of the system. Let's follow the compression process in a single-cylinder reciprocating compressor during one complete revolution of the crankshaft. Starting with the piston at the top of its stroke, or at top dead center, the piston begins to move downward as the crankshaft rotates. Because both valves are closed, the downward moving piston reduces the pressure in the cylinder. As the pressure in the cylinder falls below the low side pressure in the suction line, the pressure difference opens the suction valve, letting refrigerant vapor flow into the cylinder. The piston continues down and pulls in more vapor until the cylinder is filled with low-pressure vapor at the bottom of its stroke. Once past bottom dead center, the piston begins its upward stroke. The suction valve closes. As the piston moves up, it reduces the volume of the space in the cylinder, increasing the pressure of the vapor. When the pressure in the cylinder exceeds the high side pressure in the discharge line, the pressure difference pushes the discharge valve open, letting the compressed vapor flow out of the cylinder. This continues until the piston reaches the top of its stroke and most of the compressed vapor has been expelled into the discharge line. When the piston begins its downward stroke, the discharge valve closes. The complete cycle then repeats during each revolution of the crankshaft. This is the mechanical positive displacement vapor compression cycle using a reciprocating compressor.
The work expended in compression is transformed into heat. It is possible to remove only a small portion of this heat, and as a result, the temperature of the gas rises during compression. This increase in temperature causes various parts of the cylinder to heat up to an average value that lies between the temperatures at the beginning and end of compression. In each cycle, there is an area of the cylinder that is not swept by the piston. A volume of gas remains in this area at the end of each compression stroke. This volume is called the cylinder clearance. The cylinder clearance consists of the volume between the cylinder head and the piston at the end of the stroke, the volume between the cylinder walls and the valves, and the volume due to the difference between the diameter of the piston and the diameter of the cylinder. Due to cylinder clearance, a certain amount of gas remains trapped within the cylinder at the end of the compression stroke. This gas is under discharge pressure and temperature. The subsequent suction phase can only begin when this remaining gas has re-expanded to pressure P sub A. The suction valve will not open until this pressure is reached. This causes a reduction in inlet volume. Compression occurs only in the forward stroke. Consider now a single-stage compressor. If a higher delivery pressure happens, the compression ratio is increased and volumetric efficiency decreases. Less gas is delivered to the user and the compressor capacity is decreased. The change of absorbed power with the discharge pressure is shown on this graphic. Assume an initially low compression ratio. If the discharge pressure is gradually increased, at first the absorbed power of the compressor increases due to the increase in compression ratio. As the delivery pressure continues to rise, however, the reduction in flow rate affects the power more than the compression ratio. The absorbed power reaches a maximum value and then decreases. Recycle controls capacity by recirculating a portion of the gas from the first stage delivery back to its suction. This system is suitable for multi-stage compressors and works by reducing with the recycle the quantity of gas that is sent to the second stage and beyond. The gas amount recycled around the first stage can be varied continuously. The system therefore is a continuous type control. The first stage handles 100% of the gas under capacity control, but the following stages handle only the reduced flow rate. Therefore, the efficiency of the system is good and increases with the number of stages. First stage recycle is simple and of low cost.